Alright guys, in this video I'm going to go through everything that you need to memorize for AS Inorganic Chemistry. Now before we get started, make sure you like, comment and subscribe, and also make sure you check out some of my other videos, okay? So the first bit of this section is periodicity. Now periodicity is defined as the repeating pattern of physical or chemical properties going across the periods. Now for the atomic radius, as you go from left to right, the atomic radius decreases, and this is because the nuclear charge increases while shielding stays the same. So overall there is a stronger attraction to the electrons, pulling them closer. For the first ionization energies for period 2 and 3, you need to know the general trend and also the dips. So the general trend, as you can see, is like there's a increase generally. However, there are a few dips that you need to be aware of. So the dip for period 2 is between magnesium and aluminium. So that dip is right around here. And then it's also for sulfur, somewhere around here. So then the final graph looks like this. Okay, so as we said, generally the first ionization energy increases as you go across the period, and this is because the nuclear charge increases. So there's a stronger attraction to the outer electron. Now, we did say there's a drop between the second and the third element, or the second and third group, and this is because you're removing from a higher energy level. And what I mean by this is that here you're removing from a s orbital, whereas here you're removing from a p orbital. This drop from 5 to 6 is because there's a repulsion between electrons in the same orbital. So the graph for the melting points of period 3 looks like this, and you need to be able to explain why it looks like this. So for sodium, magnesium and aluminium, they all exhibit metallic bonding. So as you move from sodium to aluminium, the charges of the cations increase, and the number of delocalized electrons also increase. So you get stronger metallic bonds. And then the reason why silicon is so high is that it's a giant covalent structure. So you need lots of energy to break the strong covalent bonds. And then all of a sudden, these all tend to drop. However, as you can see, if you look closely, this one slowly increases, then drops back down, then drops even more. And the reason for this, well, firstly, the reason why you get this sudden drop here is because the structure is simple molecular. So you need to break weak van der Waals forces. Now to explain why there's a sudden increase here, then it drops back down, is that bigger molecules have stronger van der Waals forces. You need to remember the formulas for all of these elements. So sulfur is S8, P is P4, Cl you should know is Cl2, and argon is Ar. Okay, so S8 is obviously the biggest molecule, right? That's why out of these four it has the highest melting point, and then P4 is the second largest, so that's why it has the second largest melting point, and then obviously Cl2 is the next, and then argon is the next. Now on to group 2. So as you go down the group, atomic radius increases as you're adding more shells to the atom. The melting point decreases because the strength of the metallic bonding weakens as the radius increases, because the distance between the positive ions and delocalized electrons increases, so the electrostatic forces of attraction between them weakens, and the ionization energies as you go down decreases, since the outer electrons are further away from the nucleus, and there will be more shielding, both of which weaken the nuclear attraction, and also the reactivity increases. So group 2 metals burn when reacting with oxygen, and you need to know that magnesium burns with a bright white flame. The equation for this reaction looks like this, and the magnesium oxide formed is a white powder. So if you get a piece of magnesium, sometimes it would have formed magnesium oxide on the outer layer. Before performing a reaction with a piece of magnesium, you should remove the outer layer by using emery paper, as you want to prevent a side reaction with magnesium oxide, which would affect the rate. Alright, so the reaction between magnesium and steam produces magnesium oxide and hydrogen gas. And then the general reaction between a metal from group 2 and water is... So as you change M by going down the group, the reactivity increases. So you see more fizzing and the metal dissolving faster. Alright, so the reaction between titanium chloride and magnesium is 2Ti2MgCl2. Right. Now calcium oxide is used to remove SO2, and the reaction for this is calcium oxide plus SO2 forms CaSO3. Now when you have a group 2 metal hydroxide, it would probably be a white precipitate, if it is a precipitate, and the precipitate becomes more soluble, whereas a group 2 metal sulfate becomes less soluble down the group. Now magnesium hydroxide is used in medicine to neutralize excess acid in the stomach, and the reaction for this is magnesium hydroxide and hydrochloric acid forming magnesium chloride and water. Calcium hydroxide is used to neutralize acidic soil, and the reaction for this is CaOH2 plus CO2 forms CaCO3 and H2O. And you need to know that barium sulfate is used in X-rays as a barium meal to see intestines. Now the test for sulfate ions is barium chloride solution with hydrochloric acid. The ionic equation for this reaction is Ba2 plus SO4 2 minus forms barium sulfate. Now the reason why you add hydrochloric acid is to react with other ions, such as carbonate. Now you could use other acids as well, however you want to make sure that you don't use sulfuric acid, because the sulfate ion here would give a false positive. Okay, so at standard conditions, fluorine is a yellow gas, chlorine is a green gas, bromine is a red liquid, and iodine is a grey solid. Now as you go down the group, the melting points increase, since the number of electrons increase, making the van der Waals forces stronger, and also the atomic radii increase, which means that the oxidizing strength decreases. Now for the displacement reactions, it's good to remember that a stronger oxidizing agent will displace a weaker one. Now an example for one of these reactions is chlorine and potassium bromide. So we have 2 moles of potassium bromide, and since chlorine is a better oxidizing agent than bromine, chlorine is going to displace bromine, so we get 2KCl and Br2. They may also ask you to write down the ionic equation for this, which is Cl2 plus 2Br minus forms 2Cl minus and Br2. So that's an example of one of the displacement reactions. In this table I'm going to write down all the displacement observations. So firstly, I think it's good to take note of the fact that here we have potassium chloride, and well, chlorine isn't going to displace chlorine, right? Bromine is weaker than chlorine as an oxidizing agent, and also the same thing can be said for iodine. It's a weaker oxidizing agent than chlorine, so we're just going to remain with potassium chloride and whatever this is. So we're going to remain with chlorine, we're going to remain with bromine, and we're going to remain with iodine. Okay, so there's no reaction for the top row. And then you also need to know the colors of chlorine, bromine, and iodine to predict the observations. Well, chlorine is a green solution, bromine is a yellow solution, and iodine is a brown solution. Okay, so for potassium bromide, we do know that chlorine is a better oxidizing agent than bromine, So chlorine is going to be able to displace bromine. So there is going to be a reaction there, and the Cl is going to displace the Br. Okay. Now here we have bromine reacting with potassium bromide. Well, they're the same, Br, so there's not really going to be a reaction there. And iodine is a weaker oxidizing agent than bromine, so once again, no reaction. Okay, so when chlorine reacts with potassium bromide, like we said, there's going to be a displacement, right? So because of that, we're going to form, like we did in this reaction here, 2KCl and Br2. And that Br2 is the important thing for the observation, because we need to think about the color of Br2, and Br2 is a yellow solution. And then once again here we're adding Br2, but there's no reaction, so we're just going to be left with Br2 and KBr. And once again, that Br2 is the thing that gives us the color, and Br2 is a yellow solution. And then we have iodine with potassium bromide, and we know that iodine is a weaker oxidizing agent than bromine, so like we said, there's not going to be a reaction. And then because of that, we're just left with iodine in the, like if we had a beaker, we're just left with iodine and potassium bromide, and the iodine is what gives the color. And like we can see here, iodine is just a brown solution. Okay, and then when we have potassium iodide with chlorine, well, we know that chlorine is a better oxidizing agent than iodide, so the Cl is going to displace the I, and because of this, we're going to form iodine, which is a brown solution. And then the same thing with bromine and potassium iodide, the bromine is going to displace the iodide, and we're going to form iodine, which is a brown solution. And then we have iodine with potassium iodide. Iodine is not going to replace iodide, so there's no reaction. So then the thing that gives us the color is the iodine, which is just a brown solution. Okay, so to test for halide ions, we use silver nitrate with nitric acid. So when we have F- present, we get no precipitate. When it's chloride, we get a white precipitate. With bromide, we get a creamy precipitate. And with iodide, we get a yellow precipitate. Okay, so the general reaction for this is the halide ion reacting with the silver ion to form silver halide. And then this silver halide is what precipitate we see being formed. Alright, so you need to know the reactions between the halide salts with concentrated sulfuric acid. Now, if you try to memorize them individually, there's so many to memorize and it's going to be a lot harder. What I try and do is just generalize as much as I can. So for all of the halides, they're going to form this first reaction. So we have the sodium halide with sulfuric acid, and we get NaHSO4 plus the halide in an acid, so HX. Okay, remember X can be F, Cl, Br, or I. Here the sulfuric acid is acting as an acid, and also the HX is going to form white steamy fumes. Okay, so bromine and iodine both do the second step, which is the acid that you form in step 1 plus sulfuric acid forming the halogen plus sulfur dioxide plus water. And now in this reaction, the sulfuric acid is acting as an oxidizing agent. And also you need to know that if we have bromine here, we're going to form orange fumes. And also sulfur dioxide is colorless. And then iodine also forms this last step, which is once again the acid that we formed in step 1 plus sulfur dioxide that we formed in step 2, forming H2S plus the halogen, which in this case can only be iodine, and water. So you need to take note of the fact that the H2S is going to cause a bad egg smell, and the halogen, which in this case is I2, is going to form a black solid and also purple fumes. Alright, so disproportionation is when oxidization and reduction occur for an element simultaneously. So an example of disproportionation that you need to know is chlorine with water forms HClO and HCl. Okay, so that's one reaction with chlorine and water. However, if you have chlorine and water in sunlight, you also get this reaction. Okay, and one of the uses of chlorine is in water to kill bacteria. And even though it has toxic effects, it's still used because the benefits outweigh the negatives. Okay, and the reaction between chlorine and sodium hydroxide is you form NaCl plus NaClO plus H2O. Okay, and you have 2 moles of sodium hydroxide. And you need to know that sodium chloride and sodium chlorate are used in bleach. Okay, so that's it for AS Inorganic Chemistry. I hope you guys all enjoyed it. If you did, make sure you like, comment and subscribe. And like I said before, check out the rest of my videos. Okay?